This is Project 2.4, the Unpacked 555 Timer. This project focuses on electronic circuit design featuring the 555 IC in A-stable mode and its unpacked version, or DIY, 555 chip, using other breadboard components and its application in a counting circuit. The 555 IC is a resourceful chip used in many timing and square wave generation applications. Here, it's set up in A-stable mode to generate a continuous square wave signal. Using resistors and capacitors, the chip determines the frequency and duty cycle of its output. Inside, the chip uses comparators, flip-flops, and a discharge transistor to create precise time signals. In my project, the output square wave powers an LED, which blinks on and off. This is a visual representation of the oscillating signal, or the square wave signal, driven by the 555 timer. To understand the 555 IC better, I replicated its functionality of it using other components and ICs. Firstly, the LM358 dual operational amplifier. This chip serves as two comparators, each monitoring the voltage across a capacitor as it charges and discharges through resistors. One comparator detects when the capacitor voltage exceeds an upper threshold, 2/3 of the supply voltage, while the other detects when it falls below a threshold, 1/3 of the supply voltage. These comparators send signals to the next stage of the circuit, ensuring precise transitions between charging and discharging cycles. Their role is vital for controlling the time intervals and generating a stable square wave signal. Next, the 4001 CMOS IC forms an SR latch using two of its NOR gates, functioning as a simple memory circuit that toggles between high and low states. The latch receives inputs from the comparators, switching states to either charge or discharge the capacitor. Lastly, the 4069 CMOS inverter. This chip stabilizes and amplifies the latch's output signal, ensuring it is sharp and free of excess noise. The inverter output is a clean square wave that can drive other components like LEDs or counting circuits. By combining these chips, the unpacked circuit replicates the 555 timer's functionality in A-stable mode, providing insights into its internal operation. Finally, I connected the output of the unpacked 555 timer circuit to a recreated counting circuit from a project in the ACES course last year to demonstrate how the clock signal could drive other digital components and circuits. The square wave output from the 555 acts as a clock input for the 4510 BCD, or binary coded decimal counter IC. The 4510 counts from 0 to 9 in BCD format, incrementing its value with each clock pulse. This chip uses 4 internal flip-flops to store and represent the binary count, ensuring synchronous and accurate transitions. The BCD output from the 4510 is then sent to the next stage where it is decoded and displayed. The output from the 4510 connects to the 4511 BCD to 7-segment display driver IC, which translates the binary values into signals that control the segments of a 7-segment display. Each combination of binary inputs lights up specific segments to display numbers from 0 to 9. The 4511 ensures the display operates smoothly with control pins like latch enable, or LE, locking the input values and disabling functions like testing or blanking when unnecessary. Current limiting resistors are added to each segment to regulate the current flowing through the LEDs, preventing overheating or damage. Together, the 4510 counter and 4511 driver provide a clear and reliable numerical display. This project highlights the 555 timer's versatility and how to functionally replicate ICs using other components. By connecting it to a previous project, it is shown how the 555 integrates into more complex systems and circuits. From generating stable square wave signals to driving a 7-segment display, the 555 timer proves to be a key part of electronics design.